Mathematical induction. This is some of my favorite stuff because this is more proof in theory. So, mathematical induction is a method by which we can prove that things are true for all natural numbers. And the idea behind it is kind of like stepping up a ladder. If I was going to walk up a ladder, if you think about it, I could walk up really, as long as I had oxygen, I could walk up any ladder. Any ladder. I could walk any ladder. And the way I could convince you of this is I wouldn't need to actually literally walk up every ladder. I could just show you that I could walk on the first step of the ladder. And then, after showing you that I could step on the first step of the ladder, I could show you that I could move from one step to the next. And any reasonable person, if they believe I can get on the ladder and they can believe that I can move from one step to the next, they should reasonably assume that I could walk up any length of ladder. And that's effectively the idea of the mathematical induction. So in step one, if I want to show that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared for every natural number, so for n equals 1, 2, 3, all natural numbers, I only need to show I divided this packet into 4 steps. The first step is to show that this is definitely true for the first step of the ladder. Prove that you can get onto the ladder. So that's what we would call the base case. That's what BC stands for, is base case. And in the base case, which is n equals 1, showing it's true for n equals 1, notice that the left-hand side would just be the number 1, and the right-hand side would be the number 1 squared, which is equal to 1. So the left-hand side and the right-hand side are both 1. Then we have an assumption statement. So in the second stage, called the inductive hypothesis, here we have to assume that the statement is true for some number k. And we already know it's true, right? We know it's true for 1, so we know it's true for some numbers, but we need to assume that it's true for some numbers. So we say here usually, assume 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared. And notice I can't say for all, because that would be assuming what we're trying to prove. So here I just say it's true for some k that is a natural number. And it is true for some k. It's true for 1, like we showed. Now, what we do in step 3 is we hope that we can show that this statement is true, more generalized, in the k plus 1 case. So here I usually start off with in the inductive step. This is called the inductive step. I'm going to say, notice 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. Those were the first k. Now I'm going to substitute k for k plus 1. 2 times k plus 1 minus 1. And I'm not going to make any assumptions here. I'm just going to work with this and see what happens. So I get 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2k plus 2 minus 1. And then from here, I said in the assumption that this was equal to k squared. So this becomes a k squared plus a 2k plus 1. And remember, I knew that this is true for some k because it's true for 1. What is k squared plus 2k plus 1, though? That is k plus 1 quantity squared. So what's interesting about that is that when we added up the first k plus 1 terms through k plus 1, we ended up getting this exact statement with a k plus 1, right? K plus 1 squared. So that shows that once you're on one step of the ladder, you can totally move to the next step of the ladder. And therefore, the conclusion on these is just to state, so 1 plus 3 plus dot 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 plus 2n minus 1 equals n squared for all natural numbers n. And that's the idea of mathematical induction. So let's try that again on this problem. In the homeworks, when I do my solutions on the online, I'm only going to use the inductive step because the base case, the induction hypothesis, and the conclusion are usually generally pretty trivial, right? So we'll do this one full and gory detail, then we'll do this one down here, 23, with less. But base case. In our base case, on the left-hand side, if I let n equal 1, then I'm only looking at the first term. 1 over 1 times 3, 1/3. On the right-hand side, I'm only going to replace n with 1, so I get 1 over 2 times 1 plus 1, 1 over 3. And notice that these are both the same. Base case is successful. Inductive hypothesis. Assume 1 over 1 times 3 plus 1 over 3 times 5 plus dot 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 plus 1 over 2k minus 1, 2k plus 1 is equal to k over 2k plus 1 for some k. Okay. Now the only step that really takes any work, so I'm going to do this one in green so we can see it. The only step that takes any work is the inductive step usually, which says that we have to go to 1, notice 1 over 1 times 3 plus 1 over 3 times 5 plus dot 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 plus 1 over 2k minus 1, 2k plus 1 plus the next term, which would be what we get when we take 1 over 2k plus 1 and 2k plus 3. And we want to see what happens to that, and we're hoping we get this with a k plus 1 plugged in. So let's go see. These first k terms by the inductive hypothesis are equal to k over 2k plus 1 plus 1 over 2k plus 1, 2k plus 3. So now get a common denominator. Already have a 2k plus 1, so put in a 2k plus 3 and a 2k plus 3. And we end up getting equals 2k times k, 2k squared, 3k plus 1 all over 2k plus 1 times 2k plus 3. Okay, factor a little bit. In the numerator, we have 2k, k plus 1 over 2k plus 1, 2k plus 3. So we get some nice reduction. And now strategically on the bottom, I'm going to write k plus 1. And then although it says 2k plus 3, let me write that as 2 times k plus 1 plus 1. I knew what I was aiming for anyway, so this is not much of a shock. But you'll see that these are exactly the same, right? 2k plus 2 plus 1 is exactly what that is with a k plus 1. So that completes the inductive step. And then we get to conclude. So essentially the conclusion is we good. And that's an MWO, right? Math World Order for life. We've done this problem. So in example 23, for my last example, let's just do the inductive step. This is a formula that we did in the last unit, but let's actually do it by induction. And so I'm just going to do my inductive step, which means I'm going to have to call upon my inductive hypothesis. So don't forget my inductive hypothesis, which is a plus ar plus dot 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 a times r to the k minus 1 is equal to a times 1 minus r to the k over 1 minus r for some k. We're going to try to use that in our inductive step. So in the inductive step, I have a, ar, I get up to a r to the k minus 1, and then I add on a r to the k. But I already know that this is equal to a 1 minus r to the k over 1 minus r, then this extra little bit, a r to the k. Got to get me a common denominator. So to get that, I will put in the 1 minus r and the 1 minus r. So we'll get a minus a r to the k plus a r to the k minus a r to the k times r, which is r to the k plus 1, over 1 minus r, goodbye, goodbye, a minus a r to the k plus 1 over 1 minus r. And do you notice what I get now? We're almost there. Factor out the a, 1 minus r to the k plus 1, all over 1 minus r, which is exactly that statement, but with n replaced with k plus 1. And so that's the idea of mathematical induction.